This is a report from C1, and it involved Otsura Niwa and myself when we were members of C1, and also John Harrison from C2, and a series of external experts for certain other parts of the report. There is a reference here, so it states that it is out in 2015, this year. Last night I had the final proofs for this report, so I think it will be out by the end of this year. So this is really to explore what we know about stem cells and how they respond to irradiation, because this is a report on stochastic effects. The main effect is radiation-induced cancer, so it's really all about carcinogenesis involving stem cells and how radiation affects them, and how that links in with the risk of radiation-induced cancer for humans. Now, here's the organization of the publication. There's a main section at the start, followed by a series of annexes, which are individual reviews on each of these subject areas. They were chosen as being arranged a representative range of tissues with different weighting factors, and we knew of experts who could write these reviews. And if you have any interest in any of these, finding out all about the stem cells that are at risk in these tissues, then I recommend you to skim over the aspects of those that you need. Now, first of all, I will show you a few examples of how the tissues are organized, and here is the bone marrow with stem cells at the start here, and then there are transit cells which differentiate and form these lineages of white cells, red cells, platelets, etc. So here's the scheme, and here's the histology, showing you that there are certain domains here where the stem cells reside. And they reside in small niches, and the niche is an extremely important zone where the signals are saying that either the stem cells should stay dormant, or they should replicate or respond for injury. And here's the intestine with crypts and villi, where the niche region is here near the base of the crypt. And here's the idea of a lineage of cells which are all in the crypt. Here's the skin with the histology, the lineages which are outlined here, and in vitro you can culture certain of these populations from the stem zone, and even just above that, like here with smaller clones. And on here already is the idea that it's the stem cells in the basal layer of the skin form large tumours occasionally under the right circumstances, of course, and the early progenitors form squamous cancers, and later ones form papillomas. So it isn't only the stem cells that are important, but it is mainly stem cells plus a few others. Now, all of these things can be put in a general scheme, and this applies across the board for all of the organ systems that are identified here. So there are some short lineages and long ones where you need greater specialization of the cells. And this is now well established. Now, even in 2005, it was identified here that also for leukemogenesis, you could have different types of leukemia originating from injury in stem cells or their daughter cells. And we know, for example, for the colon, the series of stages of events that occur starting from injury in the normal crypt here, and then you have early adenomas and advanced, etc., as the whole cancer progresses. Now, earlier this year, something rather startling was published, which really caused us to think further about risk for radiation and stem cells. This is a paper which appeared in Science showing that all these blue observations here and my dashed line showing that for the total stem cell divisions over a lifetime of 80 years versus the risk of spontaneous or naturally occurring cancer in humans from the US SEER database, there was a correlation. And this thing on the x-axis here is the estimates of the number of stem cells multiplied by the number of divisions that they undergo over a lifetime. So these are replication errors, if you like, which are occurring in the whole stem cell population over a lifetime for specific tissues. Now, that is the first time ever that such a biological mechanism has been shown to apply for spontaneous cancers in humans. It's been heavily criticized in the literature because, for example, you can see there, I think that there are 1, 2, 3, 4, 5 observations there for osteosarcoma in different regions of the body, whereas for the other things that there's a single observation. So those points for osteosarcoma are strengthening, that at the end of the spread, they're actually strengthening that correlation. But on the other hand, if you put a single observation there, not 5, you still have a strong correlation. And the p-value is something like 0.00 something. So it's an extremely strong correlation. Now, there are no observations there for radiation-induced cancer, but what would you expect? Well, if you use a relative risk model and realizing that it's a log-log plot here, all the observations for a certain dose of radiation would move upwards, but on average, the whole curve would shift upwards. Now, does that actually happen or not? Well, that has been looked at recently, and here is the answer. Now, the answer isn't in the publication because it's only a recent thing, and it hasn't been published in time for the actual publication. But if you take the Japanese data and you use the mixed model, which is preferred by ICRP or beer 7, I think you can see that it isn't significant correlation. So for the evidence that we have at the moment, there has no really hard evidence that replication errors are the dominant thing for carcinogenesis. So what else is there? Well, there are other mechanisms that you can speculate on. And here's a mechanism that the immortal strand hypothesis, which has been around for a long time, where the parental strand of DNA is retained during each of the divisions of the stem cell, so that the mutations are passed on to the daughter cells, which are lost in the normal way, and the parental strand is retained. On the other hand, if it is random, then you have several cells that have the mutations in. So here's a mechanism for reducing the mutational burden from radiation. Now, this has been looked at in detail in a series of tissues, and the answer is fairly mixed. Some people find it, others don't, in the different tissues that have been examined. So this is rather tissue specific, you would say it isn't a general finding. Now, something else that is fairly recent is the idea of stem cell competition, where you can label the stem cells and their progeny using a molecular technique and follow what happens over the course of time from here to here to here. And if you can start off with a situation where in each of the crypts there are several stem cells, and after a certain time there's evolution of monoclonal crypts. In other words, there has been some competition going on. And if you think of Darwin's theory of evolution, which is based on survival of the fittest, here is the same sort of thing happening for single cells, that they're all fighting for survival in a sense, and the situation here is without irradiation at all. If you irradiate that situation with ionizations going over all the cells, even at a low dose, you will widen the spectrum of injury over all of the cells, so that you'll have repopulation occurring from the fittest cells that have the least amount of damage. So that is another mechanism. So what applications are there of this sort of information? Well, we will have a talk shortly about DDREF, which is, of course, composed of two different things, the DEF and the DREF, applying for different doses or different dose rates. Now, if you think that the alpha component here at low dose has been assumed in the past to be the same for acute exposures or for low dose rate exposures. But now there's some evidence that I'm certain that we'll hear about shortly that may not be the case. And here are some of the reasons for that these extra mechanisms that are coming in, which might occur more after long chronic exposures. So here's the effect, perhaps, of the DNA template retention thing and stem cell competition. And there are other things as well, which I haven't mentioned because of the shortage of time. There is, for example, adaptation, where cells and humans, perhaps, exposed for long periods of time at low dose rate, have some form of adaptation, so that they adapt to the conditions there, and their stem cell systems may be better able to tolerate those low dose rates. That would also be a feature here. There's also genomic instability, which has been researched a lot, where after many generations of cells, all of a sudden the genome becomes unstable and injury is expressed, and that has been proposed as part of the carcinogenic process. So the result is that there are several factors here that may influence what actually happens during chronic exposures. Something else is the age effect, and we know that children are more sensitive, and it has been explained in the past as to rates of cell proliferation, but perhaps there are other things as well that are important here with these stem cell divisions. So that is another implication, if you like, of this sort of mechanistic stuff. So the summary and the conclusions are listed here, and it's really just a summary of what I've been speaking about. And this is something that has popped out of the stem cell work as well, and I think you can realize that it isn't specific for stem cells, but it's something that arises out of the models which are used, that health promoting actions like stopping smoking might actually reduce the risk from radiation in smokers. So here's the summary of the evidence that I've been describing. And last, I can show you that one, which is future research. The first 5 items are really for research work, and I think I can mention here that around the world there are people who are researching some of these things. And for instance, the largest research program that I know of is the Euratom Risk IR project, which is all about radiation effects on stem cells. That is providing €8 million over 4 years for this sort of work. Now, ICRP is also providing support for these publications on this sort of mechanistic work. And I think that for ICRP as a whole, number 6 is the thing for them, because somehow I think it is important that these sorts of mechanistic things are brought in to support the guidelines of ICRP, which of course are based on the epidemiology of human populations. But humans are populations of cells involving stem cells as well. So the actual evidence from the stem cells helps to interpret or support the human data. And as the clock has reached 0, I will stop. Thank you, Malcolm.